All right, so here we go in level 4.5. Just thinking back a little bit to section 4.1. In 4.1, they gave us the factors or the zeros, and from that we were looking to build a graph and to possibly write equations based on the factors. And in this section, we're going to go the other way. We're going to look at polynomial equations or functions, and we are going to do lots of factoring and finding the zeros or the solutions or the roots from the polynomial equations. So just a reminder, we're going to use lots of division, and I prefer to use synthetic division to help us. I think that's kind of a shortcut. So we're going to be doing a lot of that. But before we get to that point, we're going to look at a few theorems. So first we have the remainder theorem. And it says let f be a function, a polynomial function, and f of x is divided by x minus c. Then the remainder is f of c. All right, so what that means is if we divide by a linear binomial, which means to plug in c to find the remainder. Plug in c to find the remainder. All right, so really what this means is if we look at this polynomial function here, and here our c value is our 0. So our c value is 3, and that's our 0 here. If I find f of 3 in this polynomial function, that will be the remainder. So if I just do 3 to the third power minus 4 times 3 squared minus 5. And I'm just going to calculate what this is. So 3 to the third is 27, minus 3 squared is 9, times 4 is 36, minus 5, and I'm going to get 14. 27 minus 36 minus 5 is negative 14. If I were to divide by x minus 3, and we're going to use synthetic division here, so if I take 3 here, oops, put that a little bit lower, and I write my coefficients in order, I have a 3, 2, and I'm missing an x term here, so I'm going to have to hold the x term with a 0, and then the constant. So I have a 1, a minus 4 for x squared, 0x, and minus 5 for my constant. If I bring down the 1, I get 1. 3 times 1 is 3. Add down, I get negative 1. 3 times negative 1 is negative 3. Add down, I get negative 3. 3 times negative 3 is negative 9, and I add, I get negative 14. So this is just showing that this is the same thing. So if I want to find out what the remainder is, if I am dividing by x plus 2, same function, I'm going to plug in negative 2, because that's the number I would subtract from x. That's my 0. So if I plug in negative 2 into my function, I'm going to have negative 2 to the third power minus 4 times negative 2 squared minus 5. So this would be negative 8. And this is plus 4 times 4, that's minus 16, and then minus 5, and that gives me negative 29. All right, so if I do synthetic division, just showing you that that should be the remainder I get, I'm going to take negative 2, and I'm going to have my coefficients are the same coefficients over here. So 1, negative 4, 0, and negative 5. Bring down 1. Negative 2 times 1 is negative 2. That's negative 6. This is positive 12. Add down, I get 12, and this is negative 24. Add these together, I get negative 29. So this is just showing we've got two ways to find our remainder. We can plug in what the 0 is into the function, or we can do synthetic division. So then we have this factor theorem. It says let f be the polynomial function, just like we had before up here, and then x minus c is a factor if, and only if, f of c is 0, or I get remainder 0. And if I get remainder of 0, it is a factor. So what does that mean? If you plug in c, and the remainder is 0, then x minus c is a factor, and c is a 0. All right, so it says to use the factor theorem to determine whether the function that is here has this as a factor. So we're going to look at the 0 here, and the 0 is positive 1. If I do f of 1 in here and get a 0 for the answer, then x minus 1 will be a factor. So if I do 2 times 1 to the third minus 1 squared plus 2 times 1 minus 3. So this would be 2 minus 1 plus 2 minus 3. And here I get 0. So I can say that, I'm running out of room here, x minus 1 is a factor. All right, so now let's try x plus 3. So I can either plug in negative 3, because that's my 0 here, or that's my c value. I don't know if it's a 0, but the number subtracted from x is negative 3. And I can find f of negative 3, or I can do synthetic division and look for a 0 remainder. But if I plug in negative 3, I have 2 times negative 3 to the third minus negative 3 squared plus 2 times negative 3 minus 3. So this would be negative 27 times 2. And negative 3 squared is 9, so I'm going to subtract 9. And then I'm going to have positive 2 times negative 3, that's a minus 6 and a minus 3. So I can tell right away this is going to be a negative number, and I'm keeping to subtracting more negatives, so this is not going to equal 0. Okay, no matter what I add them together, it doesn't matter what this equals, I just know it's not 0. Here's another theorem. It says a polynomial function cannot have more real zeros than its degree. So if I look at this function up here, this function is a third degree, and that means it can have at most 3 zeros that are real numbers. Okay, so usually we think of our factors as, or our zeros as being integers, but they could also be fractions, and any kind of number that's a real number. All right, moving along. Now we have the Descartes rule of signs. Okay, so the rule of signs tells us, and by the way, this is invented by a famous French mathematician, René Descartes, or Descartes, but he did some studying about polynomial functions, and he discovered a pattern looking at sign changes in a polynomial. So here we have a polynomial that's in standard form, and we want to know how many sign changes are there in this polynomial. In sign changes, we're talking about the coefficients. This one is negative to the next one is positive. So this is a sign change. Then I go from positive to positive. The sign did not change, but here I go from positive to negative, and then I have negative to negative. So this is going to tell us, it's going to tell us how many zeros we can have in a function with degree 7. All right, so here I would have 2 sign changes. Okay, so that's for f of x. If I look at f of negative x, basically if I plug in negative x, anywhere I have an odd exponent, the sign is going to change because I would be multiplying by an odd number of negatives, and then if I have a negative, it will be changing to positive. So if I have a negative x to the 7th power, that would be negative x to the 7th times negative 3. That would give me positive 3x to the 7th power. If I have an even exponent, I'm going to have an even number of negatives when I put this to the 4th power, so that would be positive, so my sign will not change. So this is still going to stay 4x to the 4th power. Here's another even exponent, so an even number of negatives is positive times a positive, it stays positive. And then here's an odd exponent, so this would be a negative times a negative is a positive, and then a -1. So if I look at the sign changes here, I go from positive to positive to positive to negative. So this is the only sign change I have, and this is one sign change. Okay. So the next one, they're asking us how many sign changes are there in this polynomial. All right, so I'm starting off with positive to negative, so that's 1. Negative to positive is another. Positive to positive stays, positive to negative, and negative to positive. So this is 4 sign changes. And for f of negative x, If I plug in negative x, remember if it's an odd exponent, the sign in front of it will change. So to the 5th power, I'm going to have a negative x to the 5th, minus x to the 4th, that stays the same. X to the 3rd, I'm going to change my sign, minus 3x to the 3rd. X squared will stay the same, plus 9x. Here's a negative, so I'm going to change my sign here, so that's plus x, and then plus 5. All right, so if I look here, the only sign change, I start negative to negative, negative to negative, negative to positive. So here's where I have a sign change, and then I have positive, positive, and they stay the same. So this is one sign change. So what Descartes found that is if we have a polynomial that's in standard form, the number of positive zeros or roots that we have is either equal to the number of variations of the coefficients of x or an even integer multiple less than the number of variations. So what that means is if we have 5 sign changes, then we can have either 5 or 3 or 1 positive roots. Okay, so if we have 4 sign changes, we can have 4 or 2 or 0 positive roots. Okay, so we start with the number of sign changes that we have, and then looking for multiples less than the number of variations. So that just means I can have 5, or I'm looking for the other odd numbers less than 5, 5 or 3 or 1. If I have 4 sign changes, I'm looking for the other even numbers less than 4, which could be 4 or 2 or 0. All right, so this tells us how many positive roots we have. So if I go back up here, if I have 2 sign changes, I could have 2 or 0 positive roots, or positive zeros. So my zeros could be positive 1, positive 2, positive 3, but I can have at most 2, or I can have none positive roots. Then it says the number of negative real roots, I'm looking here, the number of negative real roots is either equal to the number of variations of the sign change, so how many sign changes are that, or even integer multiples less. So if I have 5 sign changes for f of negative x, then I could have 5 or 3, or 1 negative roots. Okay, so here I just have 1 sign change, so I can have, or I will have 1 negative root. So one of my zeros is going to be negative, and either 2 or 0 of my negatives will be, or of my zeros will be positive. All right, so down on example 3, okay, let's kind of look at what we have here for a minute. So I have my highest power is 7. So I have at most 7 real zeros. So I could have 7 solutions. All right, so if I look for my positive zeros, so zeros that are positive means I could have, I'm going to look at the sign changes. So I'm going to look at the sign changes of f of x. So here I start with a positive 4, positive 3, positive 1, positive 2. I haven't had any sign changes yet until here. So positive to a negative to a positive, 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 positive. So here I have 2 sign changes. That means I can have 2 or any other even number less than 2, 0 positive roots. Two or 0 positive roots. If I want to look for my negative roots or my negative zeros, I need to find f of negative x. So f of negative x, remember negative x, if I have an odd exponent, I'll change the sign. So this is an odd, so I'm going to make this negative 4. This is positive, or 4x to the 7th, plus 3x to the 6th. That didn't change. A negative exponent here, so this sign will be minus x to the 5th. Even exponent here, so that stays the same, 2x to the 4th. Odd exponent here, so I'm going to change from negative to positive, x to the 3rd. Even exponent stays the same, plus 9x squared. Odd exponent, that would be minus x, and then plus 1. So now we'll look for the sign changes. Negative to positive, there's 1. Positive to negative, there's 2. Negative to positive, there's 3. Positive, 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 here's 4, and here's 5. Okay, so anytime my sign changes, I'm counting. So here's 5 sign changes. And that means I can have either 5 or 3 or 1 negative roots or zeros. Okay, so we're going to kind of put that all together here. One more thing though. We have another big theorem. The rational root or the rational zeros theorem. This is going to tell me, what we just looked at is how many roots could we have. The rational roots theorem is going to give us some possibilities of what those roots are going to be. And we looked at this a little bit earlier in section 1, where this is just a polynomial. We've got a coefficient times an x to some power. Here's another coefficient times the x to a power less than this. And then we keep going until we get some constant coefficient here, and then equals 0. So what we're going to do is we're going to look for solutions or roots of these equations. So when we start off with a polynomial in standard form, it's kind of hard to look at this one and say, but if I go back and I look at maybe one before, the coefficient of the first one, we're going to say, is a q variable, and the coefficient of the last one is going to be the p variable. So we're looking at the leading coefficient and the ending coefficient of a polynomial. And we're going to take those numbers and factor them, and we're going to look for possible roots that could be factors. So what does this mean? Okay, what does this mean? This means I'm going to take all the positive and negative p factors. So p is the last term. And I'm going to take all of those factors. This will make a lot more sense in a minute. And divide it by plus and minus q, which is the first term, and a list of all those factors. All right, so here's how this one works. If I look at this polynomial here, my p value is my ending value, so p is 6. My q value is my leading coefficient, so q is 2. And what I want to do is I want to factor these. So all of the factors of 6 are 1, 2, 3, and 6. And I'm going to divide these. And I can have a positive or a negative value there. And I'm going to divide these by positive and negative values of the factors of 2. So the factors of 2 are just 1 and 2. So I'm going to take each of these numbers on top and divide them by the numbers on bottom. So this gives me a list of possible factors, positive or negative. I have 1 divided by 1 is 1, 2 divided by 1 is 2, 3 divided by 1 is 3, 6 divided by 1 is 6. Then I'm going to take each of these numbers on top and divide them by 2. So I have 1 divided by 2, I could have a 1/2. 2 divided by 2 is 1, that's already there. 3 divided by 2 is 3/2. And then I have 6 divided by 2, which is 3. So these are the possible numbers that could be potentially zeros or solutions of this polynomial. Okay. So then it says find all the possible rational x-intercepts. That's the same thing, the solutions, the intercepts, the zeros, the factors that come from this polynomial. All right, so in part B here, my p value is the ending term is 12. My q value is 1. All right, so if I find all the factors, I have plus and minus. I have factors of 12, 1 and 12, 2 and 6, 3 and 4, and that would be all of those factors. Factors of 1 is just 1. So my potential zeros are all of these numbers divided by 1. So this is positive and negative 1, 2, 3, 4, 6, and 12. These are potential zeros right here and up here. In part C, all the possible rational x-intercepts. So looking for zeros again. My ending number p is 5. My q is 2. So I'm going to look for all the factors of 5. That's just 1 and 5, and plus and minus. And then I'm looking for my factors of 2, which is 2 and 1. So if I put all my combinations here, actually I kind of like 1 first, but I have 1 over 1 is 1. So I have plus and minus 1. 5 over 1 is 5. 1 over 2 is 1/2. And 5 over 2 is 5/2. So altogether, I'm going to have 8 possible real number zeros. Okay, 2 of each, positive and negative of each of these. So then the last one tells us to use all the rational, or to use the rational roots test to find all the possible rational zeros. That's the same thing as the x-intercepts, or the solutions or the roots of this polynomial. So here my p-value is the end, that's 30. My q-value is the beginning, which is 6. Now these have lots of factors to them. If I factor 30, I'm going to have 1 and 30, 2 and 15, 3 and 10, 4 doesn't go into it, but 5 and 6, and now I have them all. So there's a lot of factors here. And then I have 6, which is 1, 2, 3, and 6. So I'm going to do every possible combination of any of these numbers, positive or negative, divided by any of these numbers. All right, so I'm going to make a list of these. I'm going to start down here. So I'm going to divide every one of these numbers divided by 1. So I have 1 divided by 1, 2 divided by 1, 3, 5, 6, 10, 15, and 30. All of these numbers divided by 1, that's what I get. Then I'm going to divide by 2. So I have 1 divided by 2 is 1/2. 2 divided by 2 is 1, already there. Then I have 3 divided by 2, 5 divided by 2, 6 divided by 2 is 3, 10 divided by 2 is 5, 15 divided by 2, and 30 divided by 2 is 15. Now I'm going to divide all these numbers by 3. 1 divided by 3 is 1/3. Then I have 2 divided by 3, that's 2/3. 3 divided by 3 is 1. 5 divided by 3. 6 divided by 3 is 2. 10 divided by 3. Then I have 15 divided by 3 is 5, and 30 divided by 3 is 10. Now the last thing is I got to divide by 6. So I have 1 divided by 6, 2 divided by 6 is 1/3, 3 divided by 6 is 1/2, 5 divided by 6, 6 divided by 6 is 1, 10 divided by 6 would be 5/3, which is here. 15 divided by 6 would be 5/2, which is here. And 30 divided by 6 is 5. So these are all the possible rational roots that could be had for this polynomial. And how we figure out which of these will actually work is basically by trial and error. And that's what we're going to actually do next. We're going to put all of this together. Okay. So to find the real zero roots of the polynomial functions, okay, the first thing we're going to do is look for the degree of the polynomial to determine the maximum number of zeros. All right, so here is 5th degree. I'm going to write this up here because this is not a lot of room. 5th degree. So this is 5 real zeros. Then we're going to use our rule of signs to determine the possible number of positive zeros and negative zeros. All right, so for the positive zeros, I'm going to look for sign changes. So this is positive, so positive to negative, that's 1, 2, 3, 4, 5. So I can have possibly 5 positive roots. So there's 5 sign changes. Let's write that first. 5 sign changes, which means I can have 5 or 3 or 1 positive zeros or roots. If I look at my negative zeros, I need to find f of negative x. Okay, so before I can find the sign changes, I need to plug in f of negative x here. So remember, odd exponents, I change the sign. So f of negative x, I'm going to have negative x to the 5th, and then minus 5x to the 4th. Here's a negative exponent, so I'll change the sign, so that it'd be minus 12x to the 3rd. This is a positive, or an even exponent, so it stays the same, minus 24x squared. Odd exponent, change the sign, minus 32x, and then minus 16. So now let's count my sign changes. Here I go, negative, 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 negative. So I have 0 sign changes. So when I have no sign changes, that's telling me I'm not going to have any negative zeros. So I am only going to have positive zeros. All right, not going to have any negatives. So that's going to be handy when I am finding my rational roots. So that's in step 3. I'm going to use the rational root theorem, and I'm going to look for my p's and q's, or my p and q. My p is the last term, which is 16, and my first term is 1, and I'm only looking for positive numbers because I have no negatives. So factors of 16 are 1, 2, 4, 8, and 16. Divided by 1, so these are my possible roots. So now it's just kind of like a trial and error type thing. So I'm going to start with 1. I'm just going to start and see if 1 would be a solution. So I'm going to start with a 1, and then I'm going to use synthetic division with these coefficients. So I'm going to have, I'm looking back at my notes here, so I'm going to have 1, negative 5, 12, negative 24, 32, and 16. Those are my coefficients for all of these. I'll bring down the 1. 1 times 1 is 1. Negative 5 plus 1 is negative 4. Times 1 is negative 4. Add down, I get 8. 8 times 1 is 8. Add down, I get negative 16. 1 times negative 16 is negative 16. This is positive 16. 1 times, all right, something's not right here. Yep, I missed a sign here on my last 16. And 1 times 16 is 16, and I was expecting this to be a 0, just because I did it ahead of time and I knew. So I did just miss that last sign. So this tells me because I have a remainder 0, that x minus this number, or x minus 1, is a factor. And it's a factor of the polynomial. And if I were to write this down, I would have, this would be my constant term, x to the first, x squared, x to the third, x to the fourth. So this would be 1x to the fourth minus 4x to the third plus 8x squared minus 16x plus 16. So if I multiply these two together, I would get back to my original function. So let's see if 1 is another factor, or if this has multiplicity. So these coefficients here are the same as these here, okay, without this. So I'm going to try 1 again, just using these coefficients. So I have 1, I'm going to bring this down. 1 times 1 is 1. Negative 4 times 1, or plus 1 is negative 3. 1 times negative 3 is negative 3. 8 plus negative 3 is 5. 1 times 5 is 5. Negative 16 plus 5 is negative 11. 1 times negative 11, add down, I get 5. So my remainder is not 0. So I won't have another factor of x minus 1. So we did x equals 1. How about x minus 2? So I'm going to take 2 and do synthetic division. Now I'm going to use these numbers again, okay, because I'm still trying to break down this polynomial. So I'm going to use 1, negative 4, 8, negative 16, and 16. Okay, and I'm going to test to see if 2 is a 0. So I'm going to bring this down. 2 times 1 is 2, negative 4 plus 2 is negative 2. This would be negative 4, and this is 4. 2 times 4 is 8, so this is negative 8. 2 times negative 8 is negative 16, remainder 0. All right, so that tells me that x minus 2 is a factor, and I would multiply that by, this would be an x to the third minus 2x squared plus 4x minus 8. All right, so let's test to see if we have another factor of x minus 2. So I'm going to try synthetic division again with another 2. Bring down this number. So 2 times 1 is 2. Add down, I get 0. 2 times 0 is 0. Add down, I get 4. 2 times 4 is 8. Add down, and I get 0. So I have another factor of x minus 2. And what I have left here is x squared plus 0x plus 4. So this is now x squared plus 4. Okay, this one I broke down into x plus 2 and x squared plus 4. But I know that this cannot be broken down. So what I have here is a factor of x minus 1, x minus 2 to the second power, and an x squared plus 4. All right, so this is completely factored. My real zeros are x equals 1, x equals 2, x equals 2. So there's 3 positive, I'm going to go back up here, 3 positive zeros. Okay, this, if I were to set this equal to 0 and find the zeros, would not be a real number. This would be an imaginary number. All right, so these are my real solutions. We're going to do one more. This one is not long, and actually this is just a repeat of that last problem, that part B. So we're going to do part C, and then we're going to be done. So for part C, we want to first determine how many possible real solutions can I have. So this is degree equals 4. So at most 4 real solutions. Okay, so then what do? We look back, and step 2 is to do the rule of signs. Okay, so we can get 4 zeros. Rules of signs will tell us how many positive or negative solutions we'll have. So if I find f of x and the sign changes, if I look here, this is positive. Positive to negative is a sign change. Negative, positive, positive, negative, and then negative, negative. So here I have 3 sign changes, which means I can have 3 or 1 positive roots. Now I'm going to find f of negative x. Okay, so first I'll rewrite this polynomial. Even exponent, my sign stays the same, so I have x to the 4th power. Odd exponent, I'm going to change the sign, plus x to the 3rd. Even exponent, sign stays the same. Odd exponent, x to the 1st, I change the sign, that's plus 4x, and then I have minus 8. So if I look for my sign changes here, I have positive to positive to positive to positive to negative. So I have 1 sign change, which means I have 1 negative root. All right, so I can have at most 4. 3 of them or 1 of them could be positive, and then 1 of them is negative. So if I look at my P's and Q's now, my P value is 8, and I need factors of 8. My Q value is 1. Now this could be positive or negative. Factors of 8 are 1, 2, 4, and 8. So I'm going to divide by 1. So these are my possible zeros, potential zeros. So now I'm just going to try and choose. I know I'm going to have 1 negative and at least 1 positive. So let's just start with the positive and let's just try 1. And I'm trying 1 with synthetic division, and I'm going to have a 1, negative 1 for my coefficients, 2, negative 4, and negative 8. Bring it down, I get 1. 1 times 1 is 1, add, I get 0. 1 times 0 is 0, add, I get 2. 1 times 2 is 2, add, I get negative 2. 1 times negative 2 is negative 2. This is negative 10, so 1 is not a 0. Let's try 2. So I have 2, and my coefficients stay the same. 1, negative 1, 2, negative 4, negative 8. Bring down 1. 2 times 1 is 2. add, I get 1. 2 times 1 is 2. Add, I get 4. 2 times 4 is 8. Add, I get 4. And 2 times 4 is 8. Add, I get 0. So this tells me that x minus 2 is a factor and 2 is a 0. Now I'm going to try and test for multiplicity. So I'm going to try another factor of 2, and here I would have a polynomial with these coefficients. So I'm just going to keep these coefficients here, bring down the 1. 2 times 1 is 2. 1 plus 2 is 3. 2 times 3 is 6. 4 plus 6 is 10. 2 times 10 is 20. And I'm going to add down, and I don't get a remainder 0. So that would be 24, which doesn't work. So I still know I have a factor of an x minus 2, and these would be the new coefficients. So my coefficients now, this is my constant, my x squared, x to the third. So I have 1x to the third plus 1x squared plus 4x plus 4. So now, how about if we try a negative 1? So if we try negative 1, I'm going to put negative 1 here, and my coefficients, sorry, are 1, 1, 4, 4. That doesn't sound right. 1, 1, 4, 4. Yep, that's right. So if I try negative 1, I have 1 down here. This is negative 1. Add, I get 0. Negative 1 times 0 is negative 1. Add, I get negative 3, and something is just not right. I'm going to go back and check. I have x to the third, x squared. All right, I need a timeout. 1, 1, 4, 4, 0. 1, 1, 4, 4. That should work. Negative 1, add, I get 0. This, negative 1 times 0 is 0. Add, I get 4. You're probably thinking, come on, Miss Gurney, you probably saw that all the way up there. And then negative 1 times 4 is negative 4. Add, I get 0. So this tells me that x plus 1, because it's x minus negative 1, x plus 1 is a factor. And what is left is just x squared and then plus 4. And we've seen that before. This cannot be factored. So I'm left with x minus 2 times x plus 1 times x squared plus 4. My zeros are x equals 2, x equals negative 1, 2 real zeros where I could have at most 4, and one of them is positive, one of them is negative, and this is not a real number solution. So that just kind of captures everything here.